Okay, welcome to this video for Chem 161, looking at some chapter 5 content, touching on polarity for molecules. So to build towards this concept, we need to remind ourselves of some earlier thoughts that we had on smaller pieces of molecules, speaking specifically here on bond polarity. So let's remind ourselves what we know about bond polarity. So bond polarity can be determined from the separation of charge on different atoms in a bond. Okay, so that is to say bond polarity is the separation of charge on different electronegative atoms in a covalent bond. So when the sharing of electrons in this covalent bond was unequal, we would expect polarity in that bond. We previously described this using a dipole. Okay, so we had the concept of a bond dipole, and we used an arrow with a crosshair on it to help us there. Okay, so a bond dipole. Now in molecular polarity, we're going to sum many of these bond dipoles over the whole structure and respect both the magnitude of the dipole as well as its direction to determine the overall molecular polarity. Okay, so molecular polarity is determined by summing, is the key thought here, summing the polarities of all individual bonds, including strength and direction of dipoles, of bond dipoles. Okay, so let's take a look at an example to help us here. We could ask the question, is CCl4 polar? Okay, so this could be a question. And our approach to answering this is to first determine the Lewis structure. Okay, so we'll put our strategy for this question over here in green maybe. So the strategy on something like this. Step 1, determine the Lewis structure. Okay. Step 2 is then apply valence shell electron pair repulsion to determine the molecular geometry. Okay. Thereafter, we would assign bond dipoles. And recall, we base this decision, if there are bond dipoles, based on the delta, the change in electronegativity between the two elements featured in a bond. And now, some new territory for us here is to then sum these individual bond dipoles together. So sum all bond dipoles. And then you can comment on the polarity as being nonpolar or polar. Okay, so that being said, let's take a look at this example, CCl4. So based on the 4 valence electrons from carbon and the 4 times 7 equals 28 valence electrons from chlorine, you should determine a Lewis structure that is the following. And so if you have difficulty with this, please revisit some earlier videos and content on Lewis structures. Okay, so this would be the correct Lewis structure for CCl4. So we've just completed step 1. Step 2, we now consider valence shell electron pair repulsion. So this is a steric number of 4, so we'll list that, Sn equals 4. We know our electron group geometry is going to be tetrahedral, so we're going to show this by trying to establish 109.5 degree angles between each of these features. And so we'll show one of these carbon-chlorine bonds going backwards and one coming out of the page towards us with a wedge. We'll list the other 2 chlorines here. And for sake of simplicity, we're not listing lone pairs on those chlorines to indicate that here our electron group geometry is tetrahedral and our molecular geometry is also tetrahedral since there are no lone pairs at that central carbon. Good, so this is everything we've been able to do up until this point, but now commenting here on molecular polarity, we now need to apply vectors. So if you haven't worked with vectors before, a vector is a quantity. I often think about force when I'm reminded of vectors, a quantity with both quantity and direction. Okay, so it's some amount that has both a quantity to it as well as a direction. Okay. Okay, so we'll apply here vectors to describe the bond dipoles first. So we're looking to apply these little arrows. So we can remind ourselves of electronegativity. We know by intuition that chlorine's more electronegative. So if you wanted to prove that, you could go and look up the electronegativity for chlorine, and you would find that that is equal to 3.0. The electronegativity value for carbon is 2.5. And so there's a modest difference here, a delta En of 0.5, and this puts that bond into the polar category. So the individual bond dipoles would point towards the chlorine in each case. Good. 4 dipoles, 4 bonds in this CCl4 carbon tetrachloride molecule as a tetrahedron. And now we consider how these sum up together. So given that there's a separation of charge that's equal in magnitude between the central carbon to the periphery chlorine, and that is happening in the exact same quantity to each chlorine atom, we then consider if the angles around the three-dimensional space of the central carbon permit these to cancel out. Imagine, if you will, that each chlorine is pulling, like with force, on the carbon equally, but they are pulling with such an angle from one another that is matched in all 4 directions around the 3D space of this central carbon. So if each of the chlorines is equally strong at pulling, the net result is that the architecture here, nobody wins and nobody moves, therefore. Everyone is matching in strength and direction opposite to another summed vector force on the other side of the molecule. Okay, so what we see here is that analysis respecting quantity and direction shows that we have no net vector on this molecule. Okay, so no net vector, which would be the sum of the 4 individual bond dipoles. Okay, so this tells us that there is no net molecular dipole. A molecular dipole would be the sum of all the individual bond dipoles. So no net molecular dipole. So there's nothing to draw as the sum of all these 4 individual blue bond dipoles. So this tells us that this molecule is non-polar as a result. Okay, so let's try one more, and we'll try to make some room for this and leave some of the essentials on the page. And we'll look at an example where we have a net molecular dipole and a polar result. So we could ask the same question: is water, H2O, polar? Okay, so here we would be dealing with 8 valence electrons for the water molecule. You should be able to reproduce and get this correct Lewis structure as drawn here. And then when we apply valence shell electron pair repulsion to this, we note that this is also an steric number equal to 4. That means our electron group geometry is going to be tetrahedral. So I'm going to adopt a similar architecture to the one above, except oxygen is my central atom. And we'll put one lone pair over here, another lone pair over here, and we'll send a hydrogen to the back. We'll bring another hydrogen out of the page with a wedge bond. And hopefully you can see that the lone pair, putting a lobe on that to indicate that, makes this more obvious as a tetrahedral electron group geometry. And of course our molecular geometry is also based on the electron group geometry of a tetrahedron like above. However, in this case, the molecular geometry is bent since we only consider the bonded atoms. So that's a bent molecular geometry. Okay. We can apply bond dipoles. So we know oxygen is more electronegative than hydrogen. So we expect that there's going to be individual bond dipoles as such, polarizing each OH bond towards the oxygen. We also note that there's strong delta minus associated with these lone pairs that have as many electrons, 2 electrons in each location, without a bonded nucleus in place of that hydrogen. So there's a strong delta minus to the right half of this molecule as a result. Okay, so with these thoughts, we can make similar comments to what we had above. Okay, so touching on what we did above, the next step was to consider how these bond dipoles would add to one another respecting quantity and direction to give us a net vector idea. Okay, so what do we think here? Well, we notice that both bond dipoles are pointing towards oxygen, and they would sum something like along this direction, along that dashed line. Imagine you and a friend both pushing on angle on the same structure, like a fridge or something. But if you were both pushing on angle, the net result would be sort of in the middle of the two of you, and the fridge may kind of move according to that kind of sum. Okay, so there is a net direction or a net vector here. In this case, and we know that it's going to result from pushing these 2 bond dipoles ultimately along that dashed line. Not only that, we also see that the delta minus of the lone pair also is kind of speaking to a net electronegative half, which would be a lot of negative charge from the lone pairs to that right half of the molecule. So that also adds to the effect. So to draw a net molecular dipole, we want to kind of complete all those ideas. So in this case, we have evidence that we expect the molecular dipole to be pointed along this direction here, and it's going to bisect the oxygen like this, and the overall molecular dipole, respecting all bond dipoles added together as vectors do, and thinking about charges due to lone pairs, is the following black molecular dipole. Okay, so we've just drawn the net molecular dipole. And finally, if we're able to draw that, we know that there must be polarity. So this molecule is polar as a final answer. Okay, so again, the steps we've done in answering questions like, is carbon tetrachloride polar? Is water polar? First step, Lewis structure. Second step, apply valence shell electron pair repulsion to determine the molecular geometry. Remind yourself of electron group geometry as that intermediate. Then assign bond dipoles based on electronegativity values for bonds in question. And then apply a summing exercise where you respect both the quantity and the direction of those bonds in order to determine if there's a net vector. If you can draw a net molecular dipole, then you know you can answer the question as the